Welcome back to the deep dive. Today, we're tackling something huge. I mean, truly fundamental.
We really are. We're looking at a framework that claims to have, well, basically solved the biggest puzzle in physics for the last 100 years.
You're talking about the split, right? The chasm between Einstein's world and the quantum world.
Exactly. General relativity smooth, geometric, describing gravity and stars and galaxies, and then quantum field theory, discrete, probabilistic, all about particles and forces at the tiny scales.
Two different languages almost. One describes this elegant, curved stage space-time. The other describes the actors, the quantum particles doing their weird probabilistic dance.
And they just don't mesh. Trying to get them to talk to each other, finding quantum gravity, that's been the goal. The holy grail for decades.
So what's changed? What are we diving into today that claims to have found it?
Well, the source material we're looking at argues the search isn't just advanced, it's essentially over. Not by tweaking the old theories, but by rebuilding from the ground up. We're exploring the Unified Coherence Field Theory, UCFT 2.0, and its mathematical formulation. Quantized continuum physics, or QCP.
Quantized continuum physics. Okay, the name itself sounds like it's trying to bridge that gap.
It is. The core idea is incredibly bold. It says the universe isn't dualistic. It's not geometry versus quantum stuff. It's a single thing, a unified continuum of coherence.
A continuum of coherence. So what does that actually mean?
It means reality is built on coherence. The name QCP is designed to reflect this precisely. Continuum points to an underlying field, a sort of coherence curvature field. That's the geometric side.
And quantized.
That acknowledges the particle side. Discrete particles, like electrons or quarks, aren't fundamental Lego blocks. They're specific, stable, resonant patterns, eigenmodes, within that coherence field.
So particles are just ways the coherence field vibrates or organizes itself.
In essence, yes. Stable, self-sustaining patterns. It all boils down to coherence.
There's a quote in the sources that seems to capture this foundational idea.
There is. From coherence emerges curvature. From curvature, experience. From experience, the universe remembers itself.
That sounds philosophical.
It has that feel, but the claim is it's a statement of physical reality. It sets up a new order of operations. And the biggest immediate change is how it redefines gravity, or curvature.
Right. In relativity, mass tells spacetime how to curve. Spacetime tells mass how to move. That's the classic picture.
QCP throws that out, or rather, reframes it. Curvature isn't space-time bending because of mass.
Then what is it? If mass isn't the source of the warp, what is?
It's the gradient of coherence density, how steeply the level of coherence changes from one point to another. That's what we perceive as curvature, as gravity.
Whoa. Okay, so mass and energy are just indicators of where coherence is lower or organized differently.
Exactly. They're manifestations of how coherence is structured, reduced, or confined. The geometry we see is like a shadow play, revealing the underlying state of coherence.
Okay, let's try and make this more concrete. We need to talk math, I assume. In general relativity, everything starts with the metric tensor. That defines the geometry. What's the equivalent here?
QCP introduces a more fundamental object. The vacuum coherence tensor, let's call it Via-Baller. This is the bedrock. It's what links the geometry, the coherent state, and what we think of as matter and energy.
So it contains the old metric tensor within it.
It does, but in a modified way. The full tensor is given by Via-Ball C2Bal plus Chia. Let's break that down.
Okay, the Gia is the familiar metric tensor describing distances and angles. What's dollars?
Dollars is the coherence order parameter. Think of it as a scalar field, a number at every point in space and time that measures the local purity or perfection of the vacuum's coherence.
Purity, how so?
C-Dal represents a state of maximum coherence, a perfect, frictionless quantum vacuum state. No information loss, no decoherence.
And when dig is less than 1...
That's where things get interesting. When Ci11, you have coherence reduction. Decoherence happens. This is where the classical world, the world of definite measurements and distinct objects, emerges. Everything we actually see and interact with exists in regions where Ci is less than 1.
So the baseline geometry is scaled by how coherent that patch of reality is. Easy values too. That's the first term. What about the second term?
Tial is the asymmetry current. This is absolutely crucial. It's an antisymmetric tensor that encodes things like torsion and chirality, basically twists and handedness in the structure of coherence.
And why is that so important?
Because this asymmetry, this chi, is the source of all differentiation. It's where particles come from.
Okay, wait, so if chi is 0...
If chi is 0, the vacuum is perfectly symmetric. It's geometrically smooth, maximally coherent. and empty. No particles, no mass, no charge, no spin.
But when Chab is not zero,
That's when symmetry is broken locally. That broken symmetry, that twist or chirality encoded in Tra, manifests as what we perceive as particles. Mass, spin, charge, they are all consequences of a non-zero asymmetry current. They arise from structural imbalances in the coherence field.
that completely flips the script. Matter isn't stuff placed in spacetime, it's a feature of the underlying field's structure. Specifically, its asymmetry.
Precisely. And this has immediate consequences for relativity itself. This isn't just adding a new field. It changes the rules.
How so? You mentioned the metric is scaled by 2c tela 2. Let's talk about time.
Right. Relativity 2.0, as they call it, uses this coherence scaled metric. The time component is effectively 2 tellers 2. This changes the calculation of proper time, tau.
Proper time being the time measured by a clock moving along a certain path.
Exactly. The formula becomes way dt square at tc22, where beta is just velocity over $2 sedge.
So the time dilation effect, usually given by the Lorentz factor gamma, now depends on $2.
Explicitly. The coherence scaled time dilation, gamma tel, depends on the local value of $c.
What does that mean physically? Let's say I'm moving at the same high-speed battle in two different regions. One has token close to 1, the other has significantly less than 1.
You'd experience stronger time dilation in the region with lower coherence dollars?
So for the same speed, time slows down more where coherence is already reduced.
Yes. It suggests that moving through space-time, especially at high speeds, interacts with the local coherence potential.
Like motion itself spends or disrupts the local coherence.
That's a really good way to picture it. Acceleration and high velocity draw upon the vacuum's ability to maintain perfect coherence. The local value of $c sets the cost of that motion in terms of time dilation.
That's elegant. Okay, what about energy and mass? Einstein's EMEM C2D2 iconics, does that change too?
It gets generalized. The standard relativistic invariant E2, PC222, is modified. In QCP, it becomes the coherence energy momentum invariant, ET22E for M2C2.
So the rest mass energy term now also includes $2. Let's look at the rest energy, E dollars, when momentum P dollars.
If you set P dollars, you get $2 is directly proportional to the local coherence order parameter dollars.
So mass itself is tied to the local coherence level.
Yes, this leads to a profound reinterpretation. Mass is stored coherence.
Stored coherence.
The inertia, the resistance to acceleration we call mass, is a measure of how much coherence density has been successfully localized, stabilized, and trapped against dissolving back into the symmetric vacuum.
Wow. Okay, let me pause on that. Classically, mass is just there, an intrinsic property. Here, it's a dynamic state of the field, like a knot or a whirlpool.
That whirlpool analogy is quite apt. The river is the continuum, the coherence field. The stable vortex is the particle, the mass. Its strength, its energy, its persistence, its mass depends on the properties, the coherence tellers of the surrounding water. If $2 drops significantly, the vortex might weaken or dissipate.
That's a fundamental shift. What about the other universal constant, the speed of light?
Yeah.
Speed of light, Caroline. In standard relativity, it's a postulate, just stated as invariant.
In QCP, sail isn't just postulated, it emerges from the properties of the vacuum coherence field itself.
How?
It's identified as a boundary eigenvalue that's fixed by requiring something called hypergravity invariance, which relates to the overall stability framework we'll discuss. But fundamentally, Cilia arises from the vacuum's effective permittivity epsilon and permeability number.
Like in classical electromagnetism, Dowell epsilon are quite.
Exactly. But here, number and epsilon aren't fundamental constants themselves. They are derived properties that depend on the state of the vacuum coherence tensor, specifically on the coherence density, the chirality, and the torsion.
So, if those properties change, could deal change?
That's the prediction. The value we measure, approx 3 times 188 meters, is interpreted as the limit value in a sort of baseline, maximally decohered state. But QCP allows for the possibility that the effective speed of light could vary slightly in extreme environments.
Like near a black hole where coherence might be heavily distorted, or in very early universe conditions.
Potentially, yes. Tiny environment-dependent fluctuations in 7. This makes Tabron not just a defined constant, but a potentially measurable variable linked to the local coherence state. That's a huge departure and a testable prediction.
Okay, so we have this foundation where geometry, time, mass, even the dollars are all tied to this coherence field 7. Now, what governs the behavior of itself, there must be a field equation, right? Something analogous to Einstein's field equations for gravity.
Absolutely. That's the core dynamic law of QCP. the coherence field equation. It describes the interplay, the dynamic reciprocity between the coherence field dollars and the geometric curvature dollars.
It mathematically connects the large scale, curvature, and the small scale, coherence variations that source particles.
Precisely. It's a nonlinear wave equation for Tyblers. Let's not get bogged down in the exact operators, but focus on what the terms do.
Okay, so what's on the left side of the equation?
The left side describes the dynamics of the coherence field itself, its inertia, how it propagates. There's a term representing how changes in coherence ripple through spacetime, driven by curvature, and there's a term, mc2c, representing a kind of mass or inertia for the coherence field.
The coherence field has its own mass.
Sort of. It's a parameter, mc, that sets the scale for its self-organization. It prevents coherence from just spreading out infinitely. It gives the field an intrinsic tendency to form structures or maintain gradients. It provides stability.
Okay, so that's the field's own behavior. What's on the right side? That must be the interaction part.
That's where the feedback loop comes in. There are two key terms driving the change in coherence. First, there's a term proportional to the scalar curvature, $20. Let's call it alpha hour.
What does that mean? Curvature affects coherence.
Yes, this term signifies that curvature feeds coherence reduction. Higher curvature, like strong gravity, tends to locally diminish or consume coherence. Think of gravity as creating regions where $2 is naturally lower.
Okay, and the second term on the right?
That term involves the square of the gradient of coherence, something like beta noblus C22. This represents the energy cost associated with maintaining a change in coherence over space.
A coherence gradient.
Yeah.
Meaning how fast Bellers is changing from point to point.
Exactly. If coherence changes steeply a large gradient, it costs energy. And crucially, this term shows that coherence gradients source curvature. They feed back into the geometry.
So let me trace this loop. Curvature tends to reduce coherence.
Right.
But if coherence changes rapidly, a large gradient, anomalous that change itself creates more curvature.
You've got it. It's a self-regulating dynamic. Curvature eats coherence, but coherence gradients produce curvature. This constant interplay prevents runaway situations. It explains why matter clumping together doesn't just instantly cause everything to collapse. The system naturally balances itself.
This balance sounds critical. The sources mention something called the hypergravity ratio. Gamma has a measure of this balance, a universal stability bound.
Yes, gamma is fundamentally important. It's defined as the ratio of the coherence gradient intensity to the geometric distortion, essentially gamma HD to $R.
The gradient squared divided by the curvature. What does this ratio tell us?
It tells you whether a system, anything from a subatomic particle to a galaxy cluster, is stable. Think of it like the stress on a bridge versus the strength of its supports. Noble C22 is the internal stress or differentiation, and totals is the containing strength or curvature.
And there's a hypergravity stability map based on this ratio with different regimes.
Exactly, three main regimes.
But first, stable. That's when gamma is less than 1.
Right. Gamma H11 means the curvature dollar is strong enough to contain the coherence gradient C22. Coherence dominates, but it's well managed by the geometry. This is the condition for stable, long-lived things. Atoms, planets, stable particles. The system has a good safety margin.
Okay. Then there's the critical regime, where gamma is approximately equal to 1.
Gamma approx 11.1. This is the knife edge, the resonance threshold. The coherence flux, the tendency to differentiate, perfectly matches the curvature's capacity to contain it.
What happens here?
This is where transformations occur. Think mass generation, particle decay, the ignition of fusion. The system is right at the boundary, poised for change. It's a critical transition point.
And the third regime? Unstable, where gamma is greater than 1.
Gamma Ma1. Here, the coherence gradient overwhelms the containing curvature. The stress exceeds the strength. The system can't hold itself together.
Leading to?
Rapid decoherence, collapse. Think of extremely unstable, heavy particles that vanish almost instantly. Or, on a cosmic scale, this regime is linked to the formation of black hole singularities, where the structure breaks down completely because the curvature can no longer contain the intense coherence gradient. The system collapses back towards a simpler, more symmetric state.
So this hypergravity ratio gamma is like a fundamental law about identity and stability. Existence itself is about keeping this ratio in check.
That's a great way to put it. It's the mathematical expression of stability. Nature constantly tries to keep gamma at or below 1. Change happens when it crosses that threshold.
This connects beautifully to the particle side. You said earlier that particles are stable eigenmodes. Now, with mass linked to coherence gradients, this must give us a new picture of particle physics 2.0.
It absolutely does. Remember, mass my dollar comes from the coherence gradient. Specifically, QCP proposes that particle mass is proportional to the square root of the average squared coherence gradient associated with that particle structure. Propto-CN2 Wrangle 1.
So a particle with more mass requires a steeper, more intense average coherence gradient to sustain its form.
Exactly. Think about it. Maintaining a very sharp change in coherence, high gradient, is energetically expensive and inherently less stable. It's like balancing a sharper pencil on its tip.
Which naturally explains why heavier particles are generally less stable.
Precisely. Particles like the top quark, or W and Z bosons, have very high masses, corresponding to very high gradient modes. They naturally want to relax to decay into lower mass, lower gradient, more stable modes like electrons or neutrinos.
So the whole particle mass hierarchy, which seems so arbitrary in the standard model.
Becomes a spectral problem in QCP. It's the ladder of allowed eigenmodes of the coherence field, ordered by their gradient intensity. It's not arbitrary. It's determined by the fundamental solutions to the coherence field equations.
That's a huge claim. What about the forces?
Hmm.
Electromagnetism, the strong and weak forces. The standard model treats them as fundamental gauge interactions mediated by force carriers.
QCP takes a different route. It suggests that these gauge symmetries, $1 for electromagnetism, $2 for weak, $5 for strong, aren't fundamentally separate forces. They are emergent properties.
Emergent from what?
They emerge as stabilized topologies of the coherence field when the underlying universal coherence breaks partially. As the field loses perfect symmetry, see $100, certain patterns of residual symmetry lock in, and we perceive those stable patterns as forces.
Okay, let's take an example. Electromagnetism. Eudor et al. How does that emerge?
QCP interprets Eudor symmetry as arising from the need to maintain single-phase resonance continuity in the coherence field, specifically involving something called the coherence bivector.
Phase continuity, like keeping things synchronized.
Exactly. Think of electric fields as the way the coherence field enforces a consistent rotational phase or orientation across different points. Electromagnetism is the force ensuring long-range order and synchronization in the field's rotational dynamics. It maintains coherent stability over distance.
Fascinating. What about the strong interaction, SE3, the force holding quarks together and protons and neutrons?
That's interpreted as arising from a more complex, tightly bound coherence structure. It involves trinaught resonances. Think 3 interlink loops or vortices in the curvature field, operating in what can be visualized as a color space.
Trinaught resonance.
Oh.
Does that explain color confinement? Why we never see isolated quarks?
Yes, the claim is that the topology itself enforces confinement. The triply linked structure is inherently closed and stable. A single quark, a single strand of the knot, can exist on its own. It's topologically bound within that threefold resonance. Trying to pull one out just creates more resistance, eventually forming new particle pairs.
So confinement becomes a topological necessity, not just an observed rule.
Okay, what about the basic properties? Charge and spin.
Also geometric and topological. Charge is identified with the chirality, the handedness of the toroidal coherence vortex that constitutes the particle.
Handedness, like left-handed versus right-handed. Exactly. Positive and negative charges correspond to opposite helicities, opposite directions of circulation or twist in the coherent structure. Charge isn't an abstract property added on, it is the topological handedness of the vortex.
And spin, especially the weird half-integer spin of fermions like electrons.
Spin is interpreted as the internal rotation of the coherent structure, specifically involving the bivector component. Imagine the internal orientation of the coherence vortex precessing. QCP shows that for fermions, the internal structure is such that it takes a full $4 rotation, 2 complete turns for the internal state to return to exactly how it started.
Not 2 beyond, but 4 nice. That's the hallmark of spin 12 particles.
Precisely. It falls out naturally from the geometry of these trapped coherence eigenmodes. Spin is the rotational memory, the way the internal coherence structure keeps track of its orientation within the field.
It's remarkable how it all seems to tie back to the geometry and topology of this coherence field. This must lead to some overarching conservation law.
It does. The ultimate conservation law in QCP isn't just energy momentum, it's the coherence conservation principle.
Which states?
It states that the total coherence flux combining both the symmetric part, related to 2C2RLA, and the antisymmetric part, the asymmetry current tier, is globally conserved. Mathematically, this is expressed by saying the divergence of the full vacuum coherence tensor is 0. Nabla VAB equalize $.
So even if coherence is reduced locally, say, when we make a measurement or particle decays,
That local reduction in coherence or increase in asymmetry must be exactly balanced by a corresponding change elsewhere in the continuum to keep the total coherence flux constant.
nothing is ever truly lost, it just changes form or location. Coherence might convert from, say, a localized high gradient state, mass, into dispersed lower gradient forms, energy, or asymmetry might smooth out into geometry.
That's the idea. The universe as a whole maintains its total coherence budget. Local events are just redistributions within that conserved total.
Okay, let's zoom out. If QCP provides this unified picture, how does it apply to the universe on the grandest scales? Cosmology 2.0. We see this amazing large-scale structure, the cosmic web of galaxies and voids. How does QCP explain that?
QCP proposes that the cosmic web isn't just a random scattering of matter, it's a fractal projection
Projection from what?
from a higher dimensional space defined by the coherence field dynamics, something they call the 4D Finsler coherence hyperfractal phase space, or FCHP. Essentially, the 3D structure we observe is like a shadow cast by the complex fractal geometry of coherence in 4D.
Wow. A 4D coherence sheet casting a 3D shadow. And it's fractal, meaning it has similar patterns at different scales.
Yes, and QCP makes a specific prediction connecting the observed fractal dimension of the cosmic web, d-delta, to how the coupling between coherence and curvature changes with distance.
Is there a formula for that?
There is. It relates the dollars to the rate of change of the coherence curvature coupling with radius d dollars, then other df, 3 fractal m to pu dollars, and a lambda om.
Okay, what does that mean in practice? We observe d dollars to be around 2.3, right?
Yeah.
Not quite 3D filling, but more than a 2D sheet.
Exactly. Plugging DFAS prox $2.33 zik into that formula implies that the coupling lambda co must fall off roughly as $1 $4.
So the observed fractal dimension directly tells us how coherence effects weaken over cosmic distances.
That's the claim. The cosmic web structure, the filaments, walls, and voids, is the direct imprint of how this 4D coherence sheet slightly warps and decays as it projects into our observable 3D space. Filaments are where the coherence projection is strong, voids are where it's weak.
That's a stunning geometric picture. What about the dynamics of the universe, the accelerating expansion, usually attributed to dark energy?
QCP offers a different explanation. No need for a mysterious cosmological constant or exotic fluid. Cosmic acceleration is seen as a global coherence dispersion phenomenon.
Coherence dispersion, meaning
It arises from the interplay between the coherence field's potential energy, VC$, and its gradient energy, Fran plus C22. When the potential energy term dominates, essentially, when the vacuum has an inherent resistance to settling into a state of complete decoherence or perfect symmetry, it creates an effective pressure.
a pressure that pushes outwards.
Yes. This resistance to reaching a final flat state manifests as a negative pressure, leading to an effective equation of state WC2313 Thurline, which drives cosmic acceleration. Dark energy isn't stuff. It's the dynamic tension of the coherence field itself resisting complete homogenization.
Mind-blowing. Okay, this is all theoretically elegant, but physics needs experiments. How can we possibly test this? How can we measure $2 or its gradient delta sigma?
That's the crucial part. QCP isn't just philosophy. It makes concrete, testable predictions where its results should differ subtly from standard general relativity and the standard model. The key is looking for effects related to the local coherence parameter $2.
Give me some examples. Where would we look?
Okay, first, atomic clock drift. We know GR predicts gravitational time dilation.
Clocks run slower, deeper in a gravity well.
Right. But QCP predicts an additional effect because proper time depends explicitly on score T. Ultra-precise atomic clocks placed at different gravitational potentials, and thus different background coherence, the Sika dollars, should show tiny discrepancies in their ticking rates beyond what GR predicts.
A residual drift proportional to the difference in score T.
Exactly. Finding that specific coherence-dependent drift would be strong evidence for Relativity 2.0's definition of time.
Okay, what else? Maybe involving particles.
Neutrino oscillation damping. Neutrinos change flavor as they travel, oscillating between types. QCP predicts that the amplitude of these oscillations should be sensitive to the ambient coherence gradient along their path.
How so?
The prediction is that the oscillation amplitude over a distance should decay exponentially based on the strength of the gradient. Propto E kappa nabla, where kappa is some coupling constant.
So if we run long baseline neutrino experiments, say, sending beams through regions with potentially different coherence gradients, maybe affected by the Earth's core or other massive objects.
Okay, We should see anomalous damping or changes in the oscillation pattern that correlate with the expected coherence environment. This would directly link particle behavior to the coherence gradient.
That's clever. One more, maybe something really fundamental.
The most ambitious one, dynamic gravity. Remember, QCP suggests the effective gravitational coupling, let's call it GH dollar, isn't the constant dollar we usually use. It's GH equals GC22.
Joule itself depends on the local coherence. It's a huge claim. Joule is supposed to be universal.
It is a huge claim, but it's a prediction. If dollar effectively scales with 1C2 ever, then in regions of very strong gravity or potentially very high coherence variation, dollar might not be perfectly constant.
Where could we possibly measure that?
We'd need extreme precision in extreme environments, maybe observing the orbits of stars very close to the supermassive black hole at our galactic center, or analyzing signals from binary pulsars where gravity is intense. We'd look for tiny systematic deviations from GR that correlate with models of the local coherence density, SIST dollars. Detecting a varying dollar link to 262 would be a smoking gun for this theory.
This has been a lot to take in. We've gone from redefining spacetime and mass to explaining particles, forces, cosmology, all through this lens of coherence. It feels like QCP really aims for that total synthesis.
It does. It attempts to achieve that Relativity 2.0 times particle physics 2.0 unification by dissolving the old duality. No more continuous fields versus discrete particles, just coherence manifesting in different ways.
And the underlying principle holding it all together is that hypergravity ratio.
Exactly. Hypergravity invariance. The idea that stability, identity, existence itself relies on maintaining that balance between differentiation, the coherence gradient, C telemetry, and unity, the containing curvature. The universe constantly works to keep the change in that ratio equal to zero. It's the invariance of variance.
Maintaining balance through change. And if observation and measurement are part of this system, QCP must have something to say about the observer's role, right? The measurement problem in quantum mechanics is still a headache.
It does. It suggests observation isn't some external intervention that mysteriously collapses wave functions. It's an intrinsic process within the coherence field. They call it coherence differentiation.
Coherence differentiation, meaning?
When an observer interacts with a system and gains information, gains local coherence definition, clarity that process requires a corresponding change in the field being observed. It's like a trade. The observer state becomes more defined, delta C Hobbs increases locally, while the observed system loses some coherence potential or geometric freedom, delta C field decreases.
But the total coherence is conserved.
Always, delta C field. The act of knowing is part of the universe's internal bookkeeping of coherence. It demystifies measurement, making it a physical process of coherence exchange, not a philosophical puzzle.
So if we really take this seriously, if mass is stored coherence, curvature is coherence gradient, forces are coherence topologies, then the universe isn't really a collection of distinct things in an empty box.
That's the final picture it paints. It suggests the universe isn't expanding into emptiness. It's more like it's resonating within a boundless field of coherence, continuously folding and unfolding itself, expressing itself as geometry here, as matter there.
Never just a machine, but a system constantly expressing and, as that initial quote said, remembering itself through coherence.
A profoundly different view of reality. And that's perhaps the most provocative thought to leave everyone with.